Okay, so having seen limits and having calculated limits of functions for quite some time now, the next natural notion to consider is that of continuity. And this notion arguably is more important even than limits, although we need limits to define continuity. The actual definition will make it clear. Alright, now when we generate values in some kind of laboratory experiment or in the fields, say we are interested in knowing the values of some variable y in which we are interested, and that y variable depends, or its values depend on the values of some other variable x. So this is the situation of a function. And what we do in the experiment, we record some y values for some given values of x, and this creates pairs of real numbers. What we do, we plot them on a graph paper, these x comma y pairs, and then you know very well what the next step is. You join them as nicely as possible using an unbroken curve. This as nicely as possible part we are not going to discuss now because it has something to do with differentiation, derivatives. But right now we concentrate on the unbrokenness of this curve. What the curve achieves is, it tells us what these intermediate values likely are at points where we did not measure. Okay. And in doing so, we are actually assuming that the output values y vary continuously with the input values, that the output values y do not jump from one value to another value abruptly without taking on the intermediate values. That is basically the notion of continuity. Now the thing is this: so many physical processes and also other processes coming from other subjects have functions that exhibit this behavior that people in the 18th and 19th century did not think of considering any other kind of behavior that functions may exhibit. It is somewhat like a fish which is always in water, so it does not really know what water is. But say in some kind of accident, or maybe someone was fishing, the fish just came out of water for some time. Then it knew, okay, this is another state which is more hostile. The case of continuity is somewhat like that. So many functions turn out to be continuous that people tend to forget that other kinds of functions also exist. But this is what the authors say. Physicists of 1920 discovered that vibrating atoms in a hydrogen molecule can oscillate only at certain discrete frequencies, that light comes in particles, and that when heated, atoms emit lights at discrete frequencies and not in continuous spectra. So this made those other kinds of functions which do not exhibit this behavior also important. Because of this and other discoveries, and also because of heavy use of this other kind of functions, which the authors are calling discrete functions, in computer science and statistics, the issue of continuity became important not just theoretically but practically as well. Now in this section we are going to see what continuity is at a point, and we are also going to see, when we are given a function, how to test whether the function is continuous at some given point. And we will also investigate intermediate values of continuous functions. Okay, so these are the things we are going to see in this section. So now comes the definition of continuity. Although here we are saying that a function may be continuous or not continuous, but in fact even before that the notion of continuity of a function at a point comes. So that's why we have this. Continuity at a point. Now the idea of continuity of functions is actually a very general one, is a broad one which takes into account very different kinds of functions. But the kinds of functions we are primarily interested in here are the functions where the inputs are real numbers. I mean, a single input is a single real number and output is also a single real number. That is the kind of functions for which you can draw graphs using your usual xy coordinate system. And that too, the functions which in practice occur, which are of that type, usually have their domains which are either intervals of real numbers or unions of different intervals. For example, you may have a function like this, whose domain is this closed interval. Or you may consider a function like this, whose domain is the union of this half open interval and this closed interval. So that is why the kind of points that we will have to consider will be of three types: interior points, left endpoints, and right endpoints. So interior points are those points which are not the endpoints. That is probably the easiest way to explain what they are. But there is an actual definition also. For example, if you consider this domain, let us draw it on the real line. Then the point 0 is an interior point because it is neither 1 nor -1 and it is it's neither -1 nor 1 and it's also a point inside the interval. But points very close to these two endpoints are also interior points. And the thing is that for an interior point, no matter where it lies in the domain, you will be able to find an open interval containing that point such that the open interval itself is entirely contained inside that interval, that larger one which you are considering. See, for the point 0, to show that it's an interior point according to this definition, depending on the open interval, you can choose a somewhat quite large open interval. However, the more your point becomes close to any one of the boundary points, the smaller your chosen interval needs to be in order for it to be entirely contained inside this -1, 1. But if at least one such interval exists for that point, then that point is an interior point. However, note that this is not the case for either -1 or 1. That's because any open interval that contains say 1 in it, no matter how small you choose that interval to be, it cannot be entirely contained inside -1, 1 because a portion of it will always lie outside -1, 1. So that is why 1 is not an interior point. It is a right endpoint and this one is a left endpoint. Here, for example, there are many interior points, but two left endpoints -2 and 4, and two right endpoints 3 and 5, and we will have to define continuity at these types of points separately. Okay, so that's what we are going to do now. First, we come to the definition of continuity at an interior point. So this is the definition. A function f is said to be continuous at an interior point, say C, of its domain, whatever that domain is. I mean, we are of course considering the domain to either be an interval or a union of some intervals. The type of intervals we are not restricting. It can be open or closed or half open of any of the two types, but it is of that form, that is either one interval or a union of some finitely many intervals. Then at an interior point C of such a domain of some function f, we are going to say that f is continuous at C if this condition is met. The limit of f at C, that is as x tends to C, has to exist, and it has to be equal to the value of the function at that point C. Now we are going to look at these figures. In these figures, the chosen point is 0, and you see some graphs of functions we have considered. This function is continuous at 0. Why? Because there are names given to these figures A, B, C, D. I forgot to write this, E and F. In A, the function f is continuous at x equal to 0. Here C is 0. That's because if you look at the limit of f as x approaches 0, now we are we have seen this kind of things many times by now. We know that the limit is 1, because as your x approaches 0 from the left side, y approaches 1 from below 1, and as x approaches 0 from the right side, y approaches 1 from above 1, but it approaches 1. So both the one-sided limits exist, they are equal, and they are equal to 1. So this thing is 1, and that happens to also be the value of the function at 0. So this is continuous at 0. So that means the function in A is continuous at 0, but the function B is not continuous at 0. Why? That's because in this case, let me just write the things here systematically. For the function shown in figure B, the limit exists at x equal to 0, and it is also just like that one equal to 1. The left hand limit is 1, the right hand limit is also 1, but the function is not defined at 0 at all. There is no value of the function at 0, which is why we are using a white circle here in order to prevent these lines from reaching the y-axis. No, there is no such point at x equal to 0. Okay, so they get as close to y-axis as you can, but they do not touch the y-axis. So that's why this is a function which is not continuous at x equal to 0. In part C, again the limit exists, but this one fails to be continuous at x equal to 0, just like that one, although the function has a value at x equal to 0. That value is 2. So in case of B, so this is the A, figure A. For B, we have this, but f is not defined at 0. For C, again the limit exists and is 1, but that is not equal to 2, which in fact is the value of the function at 0. So this function is also not continuous at x equal to 0. However, these two types of situations are the nicest way of a function not being continuous. Why? That's because we can, in both of these situations, slightly change the function to make it continuous. Of course, the new function is not exactly the old function. What we will have to do, here we will just have to define the function at 0 to have the value 1. That will make it, in fact, just this. So it will then be continuous at 0. Here we have to redefine the function by discarding this old value and define it to have the new value 1. So again it becomes this and it becomes continuous. So this type of discontinuities are called removable discontinuity. Because you can remove the discontinuous nature of the function by redefining the function at that point. You just have to do that much to make it continuous. But the other functions that you see here are also discontinuous at x equal to 0, but they show progressively worse and worse behavior in being discontinuous. For example, we can look at this. Let us see how the situation is getting worse. What we see okay, let us first see what the function is. The function takes the value 0 constantly at all negative real numbers. That's why you see this part of the graph, which fails to reach the origin. It does not touch the y-axis. That is the purpose of this white circle, to prevent it from reaching the y-axis. That's because at the point 0, the function value is 1. And for positive real numbers also it's constantly 1. So in this case, the limit itself actually does not exist. This does not exist. So no question of limit being equal to functional value at 0. In fact, the left hand limit is 0. The left hand limit is 0, whereas the right hand limit is 1, and the right hand limit actually is equal to the value of the function at at 0, but that's not enough for continuity. So you see, here we have that kind of behavior which the authors were talking about while discussing that graph thing, that continuous functions do not jump from one value to another abruptly like this without taking on the intermediate values, but that's precisely what happened here. And because of this kind of discontinuity is called a jump discontinuity. And the definition of this is that both the one-sided limits exist at the point where you are trying to test for continuity. Both the one-sided limits exist, but they are not equal. So then the value jumps from one point to another. When that happens, then we say that the discontinuity is jump discontinuity. Now, unlike these two cases, here you cannot make things okay by simply redefining the function at one point. Okay, so it's not like this nicest bad situation. So you have jump discontinuity here, but there is this function also where we actually have one concrete function, unlike these things. Here also we have a concrete function, but here also we have another one, 1 over x square. For this one, even the one-sided limits also do not exist. Or okay, we can say that they exist, but they are not finite. They are not finite. And you can understand one thing from the definition of continuity at C, that you see, limit has to exist and be equal to f of c. That means the limit actually has to be a real number. It cannot be infinity or minus infinity. So the moment you see the function having some infinite limit at your point of interest, then automatically it becomes discontinuous. So in that sense, if you are seeking only finite limits, you can say that limit actually does not exist, in the sense that it's not a real number. So in that sense, I was trying to say that the one-sided limits in fact do not exist. In this case, this is the situation. And it is like this one because the function also lacks a value at 0. It is not, it's not defined at 0. You can try to define, you define it at 0 and say it has this value, say 1. But that won't do anything, that won't improve the situation. But the worst kind of continuity is this one. You see, at least here you know that the function has some consistent behavior very near 0, namely that the closer you get to 0, either from that side or from this side, the function just keeps on increasing and increasing in value. Here, however, the situation is quite different. This one is also discontinuous at 0. But here, the values are not increasing or anything like that. But the closer we have already seen this graph, okay, by now. But the closer you come to 0 from either side, the function oscillates between -1 and 1 so much that it does not settle at any point. So that is why, because of this increasing oscillation, the closer we come to 0, this fails to be continuous. So here you can just like you have called this one jump discontinuity. This kind of discontinuity is called infinite discontinuity. But besides jump and infinite discontinuities, you have some oscillatory discontinuities like this as well. Okay. Now, next comes, so we can now get rid of these figures. Next comes the definition of continuity at a left endpoint and then continuity at a right endpoint. And these are defined using one-sided limits. Well, there is a figure. Let us draw the figure first. I mean, I cannot, of course, possibly have all the figures pre-drawn. Suppose this is my interval whose left endpoint is A and right endpoint is B, and there is of course one interior point C. And this is the graph of my function. A function f is said to be continuous at a left endpoint A of its domain. You see, we say a left endpoint, not the left endpoint, because you have seen one example of that G where there are two left endpoints. A of its domain, if the limit of the function at A but right hand limit exists and is equal to the value of the function at A. This may be a little confusing at first because we are saying left endpoint and we are saying right hand limit. That's because you can understand that the function is not defined on the left side of A there is no value. So we can only use the values of x that are greater than A. So only this limit makes sense, only the right hand limit. So as x approaches A from the right side, the function has a limit. If that limit turns out to be equal to the value of the function at A, then we say that f is continuous at the left endpoint A. Note that we are not saying left continuous or right continuous, anything like that. Simply continuous, but this is another definition because this is another kind of point. It's not an interior point. That's why we are forced to consider one-sided limit. Similarly, f is said to be continuous at a right end point. B of its domain. Now you can guess what I am going to write. If the left hand limit of the function at B exists and is equal to the value of the function at B, and this time we are considering left hand limit because to the right of B there is no function value. We can consider only this limit. But now we can actually define left continuity and right continuity. Okay. A function f is said to be left continuous at a point C if the left hand limit of f at C exists and is equal to the function value at C, and right continuous at C if the right hand limit of f at C exists and is equal to f of C. You may note that here we are not saying what C is. Simply from the letter C we may assume that C is an interior point, but not necessarily. The thing is that here C is a point for which this limit makes sense. Here C is a point for which this limit makes sense. C may be for example here, C may be an interior point or a right endpoint. But here you cannot consider C to be a left endpoint. Similarly, here C may be an interior point or a left endpoint. Okay, so this is a new notion, that of left continuity and right continuity at a point. So from this, what can we say? From this we can of course immediately say one thing, that if C is an interior point of the domain of F, then F is continuous at C if and only if it is both left and right continuous at C. So this is just like a limit existing if both the left and right hand limit exists and are equal. But what about these things and the endpoints? You can understand what it is if you think of it carefully. Let C be a left endpoint of the domain of F. Okay, so C is something like this. Here is an interval which is a part of the domain of F. So C lies here. Then F is continuous at C. See, F is continuous at C means that definition of continuity involves only the right hand limit. So that's why F is continuous at C if and only if it is right continuous at C. Similarly, if C is a right endpoint, then F will be continuous at such a point C if and only if it is left continuous at C. Okay, so I think it's actually it's simple, but sometimes this left and right occurring together may confuse us. So if we really have to use these words left continuous and right continuous, we should be careful. Finally, let us consider two examples. In example 1, we have this function y equal to, or actually I should not have written y, but f of x is equal to the square root of 4 minus x square. Now we already know what the domain of this function is. Domain is this closed interval minus 2 comma 2. If you recall how we used to find domains, we need real number outputs. So because of the presence of this square root, 4 minus x square needs to be non-negative. That means what? That is equivalent to having 4 greater than or equal to x square, which in turn is equivalent to this, and that is equivalent to 2 being greater than or equal to the absolute value of x. You see, we are taking absolute value, and that's why we are able to lift the square just like that. X may be negative also. We cannot take simply x here. But this inequality is itself equivalent to what? X being inside this closed interval. So that's how we get the domain of the function to be this closed interval. Now if one draws the graph of this function, the graph is nothing but the semicircle. Okay, this semicircle lies between these 2 points minus 2 and 2, and of course it will go like this. It's not a perfect semicircle, freehand drawing cannot be perfect, but it's like this. So this point is also 0 comma 2, this much is 2. Now you can see that this function is actually continuous at any interior point because the graph is in one piece, or you can apply the definition also. However, the function is right continuous at minus 2 and left continuous at 2, or simply put, the function is also continuous at these 2 endpoints, but there The definition uses only one-sided limits because only they can be considered. And there is one more example. And in this next example, we consider a unit function where you have that discontinuity, which we have called a jump discontinuity. And here the function is given simply by its graph. Although from the graph itself you can clearly see what the function rule should be. And it is that function which constantly takes the value 0 at every negative real number. But the moment it reaches 0, its value jumps from 0 to 1 and then stays constantly 1 as your input is a positive real number. So it is that function. Because we are talking about the graph here, so we can write y equal to u of x. This function has been called and has been given the name unit step function. This function is, we have already seen, it's not continuous at 0, but this is right continuous at 0, because at 0 the right hand limit exists and is equal to 1, which is the functional value at 0, that is also 1, but it is not left continuous. At 0. So in this case there is no, you cannot talk about, if you simply talk about original continuity, then it's not continuous at 0, that's just it. However, if you talk about this one-sided continuities, then it is right continuous at 0 but not left continuous at 0. And to summarize the thing, what we have to do, if we are given a function and a point where we need to test whether the function is continuous, this is what we have to do. At an interior point actually, say we are given a function f and c is an interior point of the domain of f, then f is continuous at C if three conditions are true. Number 1, f of C exists. Okay, if this itself is not true, then no question of continuity at C. Number 2, this limit should exist, because if this also does not exist, just like this one, even having the functional value, there is a value at 0, but in spite of that, because the limit does not exist, the left and right limits do not have the same value. In that case also it's not continuous. And the third thing, that even when the limit exists and the function value also exists, they may not be equal. In that case also continuity fails. If these three conditions are true, then only we can say that f is continuous at the interior point. And like this, like a kind of test, you can also write conditions for testing whether a function is continuous at a left endpoint or at a right endpoint. Okay, I leave that to you. And this is where let's just stop for tonight. We will see what comes next in these things. And then of course we will have many problems that we will solve. Many of them will be left to you, but please try to solve those problems that I leave to you. There are so many problems, so many exercises that it's impractical that I solve each and every one of them here. So a significant portion of these things are left to you, but of course if you don't get anything, then please let me know immediately in the comments. And that's just it. So see you in the next upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.